There is one last thing I should say before moving on. There is a way of going back from zero groupoids to negative one groupoids as well. In fancy jargon, this inclusion of negative one groupoids into zero groupoids admits a right adjoint, which I could call pi minus 1.
Wait, hold on. Oh, wait. Left is when you take the... Oh my god. Bienvenue mes amis. I am Chef Boyarger, and in cette leçon de cuisine aujourd'hui, we will learn how to make curry. Curry is a very popular dish that can be found in many countries. To make curry, you need to make sure you have the right kind of product. Some may want to use chicken stock or tomato paste, or go crazy with the spices. But what is important is how the flavors will project themselves. This is the most universal even. One thing I love to add to my curry is coconut milk. It really helps give my curry the right consistency, kind of thick but flowy. I call it coconutinuity. If you're in a locally presentable setting, coconutinuous products are enough to make an excellent curry. However, all that really matters is that it warms the soul. If made correctly, a good curry will inspire low, steady music from within, which the professionals refer to as an internal hub. This adjunction between your product and the internal hub is the defining characteristic of a good curry. Hello, ladies, gentlemen, and the classically excluded middle, and welcome to another Khan Academy lesson. Given some recent drama on social media, it's only out of my boss's good faith that I'm being given another chance at hosting this video series. The topic we'll be tackling today is adjoints. Adjoint functors. A short and sweet summary of the intuition behind adjoint functors is that they are conceptual inverses of each other. If you've seen my video on the Yoneda lemma, you'll know that I hate these oversimplified intuitive crutches, not because they're wrong, but because they only really make sense if you already understand the concept. I've at least never been able to make good use of this analogy. It's like relating the conjugate transpose with the inverse of a matrix. For a somewhat concrete example, suppose you want to write down a linear transformation from three-dimensional real space to some humongous real vector space, like the space of continuous functions from the real numbers to itself. The stupid way to do this would be to try and manually associate to every three-dimensional vector some continuous function and then check that this association is linear. The better way would be to remember that 3D real space has a standard basis of 3 vectors, meaning that every vector in 3D space is written uniquely as a linear combination over this basis. Once you specify how these basis vectors behave under T, linearity of T helps completely determine where the rest of the 3D vectors must go. Moreover, since the basis vectors are linearly independent, any choice of continuous functions for Ex, Ey, and Ez will define a linear transformation in this way. This means that defining a linear transformation from three-dimensional space to the space of continuous functions just amounts to defining an ordinary mapping from the tiny set of 3 elements into the set of continuous functions. Of course, there's nothing special about the space of continuous functions. Defining a linear transformation from three-dimensional space to any vector space V amounts to defining a simple function from our small 3-element set into the set of points of V. This can be written more succinctly as stating that there is a natural correspondence theta from the set of linear transformations from 3D space to V to the set of functions from the set of basis vectors to the set of vectors in V. Evidently, this is not more succinct to read aloud, but mathematicians hardly ever speak. If you think back to your linear algebra course, vector spaces are determined up to isomorphism by their dimension. Well, as long as they have a dimension. Three-dimensional space is the unique vector space with 3 basis vectors. This natural correspondence reflects this uniqueness, giving us what is essentially the defining characteristic of three-dimensional space as a vector space. If any vector space U admits a natural correspondence of the same shape, then U must be canonically isomorphic to three-dimensional space. The proof of this fact falls out of the Yoneda lemma, but the point is that three-dimensional space is completely determined by having this property. In fact, this property gives us a universal property of three-dimensional space. To see this, take the correspondence and replace V with the three-dimensional space itself. The left-hand side now consists of linear transformations from three-dimensional space to itself, and in that set there's one very particular element, namely the identity map, which does nothing to each vector. Pushing the identity through this correspondence, we get a function from the set of basis elements to the set of all 3D vectors. As you might be able to guess, this function just sends each basis vector to itself viewed as a 3D vector. You may notice that this function eta looks and behaves an awful lot like the unit map of a monad, but I digress. With this function eta, we can state the universal property more concretely. For any function f from the basis vectors to the set of points of some vector space V, there exists a unique linear transformation phi from three-dimensional space into V, such that phi is in some sense a linear extension of f. Of course, this is just a categorically charged way of saying what we knew all along, but it makes you wonder, is there anything special about the set with 3 elements? Specifically, given an arbitrary set B, can we construct some kind of vector space FB enjoying a similar universal property? Now, why would I bring you all the way here if the answer was no? You can take the so-called free vector space on B, which is the vector space whose elements are formal linear combinations of elements of B. I've explained free algebraic constructions at least a couple of times already on this channel, but if you're more comfortable with colimits, the free vector space is the coproduct of one copy of the real line for every element of B, and this is no accident. In any case, rewriting the universal property of this free span construction in terms of Hom sets, we get a very tantalizing equivalence. Have we realized our adjunction? Well, almost, but I haven't said anything about functoriality. Sending a vector space to its underlying set of vectors is functorial because a linear transformation of vector spaces canonically defines an ordinary function on underlying sets. It might already be clear to you how the free span construction is functorial as well, but I think it's worth belaboring a bit how this falls out of the universal property. If we're given some plain function g from b to b prime, then since b prime embeds via eta into the free span generated by b prime, we can use g to define a function of sets from b to the free span of b prime. Therefore, by the universal property of the free span of b, we get a unique linear transformation from the span of b to the span of b prime, which restricts to g on basis elements. All in all, with functoriality established, this gives us a free vector space functor which defines the left adjoint to the underlying points functor. The general story for left adjoints is pretty much the same. The idea is that we have some functor u from D to C, and we're interested in objects satisfying an outgoing universal property with respect to u. This means for some object C, we're interested in constructing an outgoing arrow eta from C to U of some object in D where this object is universal with respect to having such an arrow. Universal in this case means that whenever C has a map to U of some other object D, then there must be a unique morphism from the universal object into D, which in some sense extends the map in C. This universal property is equivalent to establishing a natural correspondence between the maps from C to U of D and the maps from FC to D. Since we're talking about universal properties, you might wonder how this might be connected to limits and colimits from previous videos. Well, this formalism also applies to colimits for a fixed diagram shape J. I don't want to belabor how this is. You can pause or work it out yourself if you're curious and don't already know. The reason I want to bring this example up, though, is to stress that, in general, colimits of a fixed kind may not always exist. This means there's also no reason to expect that these universal arrows exist for a general U. But in the special situation where we can find such a universal object FC for every C, we can assemble the FC together into a well-defined functor f from C to D, which is called the left adjoint to U. But gee, you say. What about the universal property of a limit? As with many categorical results, we're in a buy one get one free situation, though I suppose I showed you the free one first. By simply reversing all arrows, the fact that a left adjoint is completely determined by its right adjoint tells us that right adjoint is similarly completely determined by its left adjoint. Looking back at our linear algebra example, the universal property of the free vector space of a set of basis vectors can be flipped around to give a universal property of the set of underlying vectors associated to a vector space. To achieve this, we take the opposite approach and replace B with the set of vectors underlying V. Now the right-hand side holds the identity map for the set of vectors in V. If we pull the identity map through the correspondence onto the left-hand side, then we get a linear transformation which I may call epsilon. Concretely, this epsilon is a map that takes formal linear combinations in the vectors of V and evaluates them as genuine linear combinations in V. This map may seem eerily similar to the co-unit map of a comonad, but again, I digress. As an aside, I must have been ill when recording my comonad video because wow, that was co-interesting to listen to. Which is a shame because the punchline of the video is still really cool. Anyway, what this co-unit map enables us to articulate is the universal property that whenever we have a linear transformation from a vector space with a chosen basis B into V, there exists a unique function from B to the underlying set of vectors of V such that, well, this is a bit of a mouthful. Given a function of sets from B to the set of vectors underlying V, the induced map of spans sends a linear combination of basis vectors to the corresponding formal linear combination in V. In combination with the evaluation co-unit map, this is to say that phi applied to a linear combination of basis vectors in the span of B amounts to applying f to the basis vectors and evaluating the corresponding linear combination. Peeling away all of the mathematical notation and jargon, this is just to say that a linear transformation out of a vector space with a basis B is completely determined via linearity by its behavior on the basis elements as a function of sets. But gee, you may object, isn't this interpretation exactly the same as the universal property of the span? Where's the duality? Well, given that both universal properties are derived from the exact same correspondence of Hom sets, it shouldn't be surprising at all that the intuitive interpretation is almost indistinguishable. That said, there is a bit of duality in the interpretation here. The universal property of the free span puts emphasis on the fact that you can extend an arbitrary function from a basis to a linear transformation of the vector space with that basis. On the other hand, the universal property of the underlying set of vectors puts emphasis on the fact that a linear transformation out of a vector space with a basis is completely determined by its behavior when restricted to that basis. Either interpretation doesn't offer more information than the other, of course, but it's a matter of intention. The more general picture is essentially the same. We now start with some functor f from C to D and are thinking about a universal object associated to D, with an arrow epsilon from f of that object into D satisfying an incoming universal property. In this case, the universal property is that each map from f of some object in C to D is in some sense determined by a restricted map from C to the universal object. At this level of generality, we also encompass the notion of limits. Now, if we can construct such a universal object for every D, then we can assemble this construction into a functor U, defining the right adjoint to f. Now, hopefully with this introduction to adjoint functors, I can be forgiven for my buffoonery. If you're still here, thank you for watching. If you liked what you watched, there's a free way to express that somehow. If you didn't like what you watched, but gee, that embarrassing blunder was about higher categories, not ordinary categories. Damn it. Do I have to Bienvenue encore, mes amis. C'est moi, Chief Boyarji, avec une leçon bonus. What if you wanted to enrich your curry with higher dimensions of flavor? Anyway, as with any other ubiquitous concept in ordinary category theory, there is a generalization to a higher category theory. If you don't know what a higher category is, it won't really matter, because two functors between higher categories form an adjoint pair under pretty much the same circumstance as in the ordinary case. The only thing to be wary of is that the correspondence is much weaker. But gee, you may be thinking, what about the universal properties? The higher the dimension of your category, the less you'll want to spell out the universal property. But since you insist, suppose we have a putative universal arrow epsilon from f of the universal object into D and some arrow phi from f of some other object into D. then we expect a unique f from C into that universal object, whose image under f makes this triangle commute. But hold on, there are two problems now. First, commutativity isn't a property, it's a two equivalence from the upper path to the lower path. Secondly, uniqueness isn't a property either. Rather, if we have some lift C to the universal object and its associated two equivalents, and then we get a second lift from C to the universal object with its own associated two equivalents, then these should be the same, meaning that there should be a two equivalence connecting our two lifts, making the triangle of two equivalences commute. But this commutativity needs to be exhibited with a three equivalence. Oh, but then if we have two equivalences connecting our lifts, with their own associated three equivalences exhibiting commutativity, then these should coincide, meaning that two equivalences need to be connected by a three equivalence, making the conduced triangle of three equivalences commute. That is, we need a four equivalence. But this three equivalence needs to be unique, which means that if we have another three equivalence to be connected by a four equivalence of their own, requiring a five equivalence to express coherence. And of course, the four equivalence should be unique, so given another, we get a five equivalence with coherence to six equivalence. And don't think just stop there because it's six, it goes from six and then to seven, and then six, oh my god. Anyway, there is a better way to formalize the universal properties here. You can state that the adjunction unit and counits are initial and terminal objects respectively in certain comma categories, but that's not that important right now. The point is that adjunctions don't feel that different when you go to higher category theory. Now that we're up to speed, I can finally rectify my statement about adjoints that I made in my equality video. Note that the ultimate construction of infinity groupoids as a limit of projections is still correct in that video, but the justification requires swapping lefts and rights to be correct. Now, back to the problem at hand, there are two correct things I want to say. First of all, the truncation map from n+1 groupoids to n groupoids is left adjoint to the inclusion. Secondly, this inclusion from n groupoids to n+1 groupoids doesn't admit a right adjoint at all. If the higher groupoid mumbo-jumbo didn't make much sense, but still don't want to support me by watching my other content, there isn't much lost generality by looking at the n equals -1 case. In that case, I didn't even need to talk about higher categories. When n equals -1, the n+1 groupoids just form the benign category of sets, and the n groupoids form the full subcategory spanned by the empty set and a singleton, which I will just call omega. Wait, hang on. This means that I'm assuming the law of the excluded middle, aren't I? Damn it! Anyway, knowing correctly that this map admits a left adjoint is enough to derive the map pi-1 from sets to omega. Since omega only has two elements, the adjointness condition basically says two things. Well, the two things the adjointness condition says come from the first correspondence. The second correspondence is always true by virtue of the fact that the singleton is a terminal object in both omega and the category of sets. Dissecting the first correspondence, note that it is generally impossible to write down a map from a set X into the empty set. The only exception is when X is itself empty, in which case there's only one map. Moreover, since omega is a full subcategory of the category of sets, the exact same statement holds true there. By mixing and matching the Hom sets, this tells us exactly what pi-1 ought to be. Wow, excluding the middle really makes things easy, huh? Now let's wrap things up by proving that the inclusion can't have a right adjoint. Let's make believe that the inclusion admits some right adjoint R. Again, we have two correspondences. Dual to earlier, the first correspondence is always true by virtue of the empty set being an initial object in both omega and the category of sets. As for the second correspondence, note that we can identify elements of a set Y with maps from the singleton into Y. In particular, if Y has more than one element, then so does the left-hand side of this correspondence. On the other hand, we can enumerate the Hom sets of omega, and we can see that neither of the possible Hom sets have more than one element. This makes it impossible for the right adjoint to exist at all. In fact, this reasoning generalizes to higher groupoids as well. Now that you can see how simple this error was to fix, you might be wondering why I didn't just quickly double-check this fact before making it part of the punchline of my equality video. That would make two of us. Anyway, if my laziness upsets you, it's fine. Even at my worst, I can always count on that one fan to back me up.